All right, so my name is Francis, and today I'll be talking about my research on the characterization of vibration sensitivity of one-port and two-port MEMS microphones. So first of all, I'll give you a bit of context on how this project came about. So our industrial partner, Soundskrit, developed this two-port MEMS microphone that they wanted to implement inside compact systems that were exposed to a lot of external vibration. So they wanted to know how sensitive their microphone would be to parasitic vibration. So first of all, let's go over some basic background. So what's the difference between a one-port and a two-port MEMS mic? So a one-port MEMS mic here is our traditional omnidirectional mics that we're used to. Here in blue, we have a Knowles Lazarus. And a two-port mic here is a directional microphone. And here in green, we have the Soundskrit SKR0400. So to help us understand the difference, let's imagine a sound wave hitting our microphone via the on-axis. So if you have our typical one port here, it's going to have one port exposed to the pressure of the sound wave, and the other side of the sensing element is going to be at a reference pressure in the reference pressure chamber. This is going to lead to a pressure gradient and a displacement of the sensing element, and this is how we're going to get our signal. If we expose the same mic to off-axis, a sound wave hits the microphone via its off-axis, we're going to measure the signal the exact same way. It doesn't going to change anything. So we can see that one-port MEMS mic are independent of the incoming angle of the sound wave. However, when we take a look at a two-port MEMS mic, we have two ports exposed to the sound wave, and here our two ports are in two different constant pressure lines. So in a similar fashion, there's going to be a pressure gradient, a displacement of the sensing element, and we're going to record a signal in a similar fashion as our traditional microphone. However, when we're being hit via the off-axis, we can see that both of our ports here are in the exact same constant pressure line, which leads to no pressure gradient, no displacement of the sensing element, so no signal being recorded. So two-port MEMS microphones are highly dependent on the incoming angle of the sound wave. This is actually a great advantage for a two-port mic because with the data we record, we can actually extract the sound wave direction, which is something that the one-port MEMS mic cannot do. However, one-port MEMS mic measures an absolute pressure of the sound wave, and the two-port MEMS mic measures a pressure difference inside the sound wave. And this pressure difference is fundamentally smaller than what we measure in the one-port MEMS mic. So we have these really small pressure differences that we're trying to sense. So we need softer sensing elements that are more compliant to the force they are subjected. So here, just to give you an idea, we have a one-port mic, a Knowles Lazarus, the one I showed earlier, that has a natural frequency of 39 kilohertz. If we compare this with the Soundskrit, a two-port mic, we have a natural frequency of 4.5 kilohertz. And as we know, a lower natural frequency, a softer sensing element. So we're wondering if this will increase the parasitic sensitivity to vibration. And we'd like to do so by developing a universal expression in acoustically referred terms. What I mean by acoustically referred terms is that we want to know the amount of parasitic Pascal for a certain acceleration. So there's been some previous work on this for the one-port MEMS mic. So we have Walsh and Miles here who find out that the vibration sensitivity can be estimated by using a lump mechanical bottle that is based on the membrane mass and the air mass that is coupled with the membrane. And this air mass that is coupled with the membrane often dominates the total mass of our system, so we can even neglect the membrane mass and we get a pretty good approximation. So we expanded this idea for our two-port MEMS mic. So we assumed it was a lump mechanical model taking into account the air masses and the membrane mass. And what we found is that it has a relationship that is inversely proportional to the natural frequency. This is not really surprising. We see this relationship in all kinds of accelerometers and other sensors. But this is the amount of parasitic displacement for a certain acceleration. As I mentioned earlier, we're looking for acoustically referred terms, so we're still missing a relationship to have our acoustically referred units, and that is the sensitivity to acoustics. So when we take a look at the sensitivity to acoustics, we find out that it also has a relationship that is inversely proportional to the natural frequency. Meaning that a softer sensing element will make us more sensitive to vibration, but it will also make us more sensitive to the sound wave that hits it. So when we combine them together to get our acoustically referred units, we get this equation, really simple, that doesn't rely on the natural frequency. In fact, it only relies on universal constants, such as the density of air, the speed of sound, over the frequency of the vibration itself. A couple assumptions were made here. So we still assume that the total mass of our system is dominated by the air. And we also assume that the distance between the two ports, dp here, is equal to the sum of the lengths of the air columns. So here, L1 and L2. When we compare the two-port equation with the one-port equation, we see right away that we expect two different frequency response. Here, the one-port MEMS mic is going to have a flat frequency response, and here we're going to have a frequency response that is inversely proportional to the frequency of the vibration it is subjected to. So we wanted to prove our theory and get some data to get our experimental, with our experimental setup. So we have a PC that controls a wave generator. This wave generator sends a signal through the power amplifier, which then feeds it inside our shaker table. And we designed this custom mount that can accommodate up to 2 microphones and 1 accelerometer. The microphone can be either mounted on axis or off axis. And then all these signals are recorded with the oscilloscope and saved using our PC. So all the measurements were done is we first characterized the acceleration using our accelerometer, and then we subjected our microphone to the same acceleration, and we normalized their signal with the acceleration we had recorded. So we have 4 types of microphone under test. So we have our standard 2-port mics, and what I mean by standard 2-port mic is that here we have the exact same geometry that my theoretical model was based on. We have 2 different microphones. We have the Soundskrit and the TDK, and they both have a different natural frequency. So we wanted to prove that it doesn't depend on the natural frequency, so these were the perfect microphones to test. So here we have a 2-port mic in a gasket, and we wanted to see how different geometry would affect our vibration sensitivity. After that, we have an array of 2 1-port mics. These are 2 Knowles Winfrey wired differentially using a custom array. And here they essentially simulate a 2-port mic with 2 1-port mics. And we wanted to see because how the vibration sensitivity would react, because here the air columns are going to be very different. And then finally, our traditional 1-port mics that we're all used to, a Knowles Lazarus. So when we take a look at experimental measurements, if we look at the raw vibration sensitivity, as I mentioned earlier, it should have a relationship that is inversely proportional to the natural frequency. And this is actually exactly what we see. So we have the Soundskrit here with the lowest natural frequency and their highest output power. And we have the TDK and the Armin with a slightly higher natural frequency, but a lower output signal. The acoustic sensitivity, we should see the exact same relationship, and this is exactly what we see. So we combine both of these together to get our acoustically referred vibration sensitivity, and we get our final figure of merit. So here, we see that the Soundskrit, the TDK, and the Armin all falls within the boundaries of my model very nicely, even though they have different natural frequencies. Here, the only outlier is the Winfrey array, which had a very different geometry and sensing approach, so it was expected to be slightly off my model. However, we still see exactly the same trend. That is 1 over the frequency of the vibration. And for our 1-port mic follows a constant signal and is similar to match our result pretty nicely. So to conclude, two-port mics are more sensitive to vibration, but it doesn't depend on the natural frequency at all. It depends only on universal constant when we're looking at the standard two-port geometry. That is the density of air, the speed of sound, over the frequency. So to conclude, I'd like to thank my industrial partner, Soundskrit, all my lab mates at MEMS and NRC, as well as the funding that NSERC